Okay, thanks for coming back, everybody. So this is the second session of the Neuroimaging Research Group fMRI workshop from this year. So in our first session, we talked a lot about the kind of the structure and overview of what the using Linux and high performance computing cluster kind of looked like. Um, and I know there's a couple people that are potentially joining us for the first time at this point, so that's useful as an overview of what all that looks like. So I'll mention a few of those things as we're going through as a little bit of review. Um, but in this session, what I wanted to do was to kind of go over a little bit more about the conversion of DICOM files, which is the raw form of data coming from the scanner, um, and a little bit about the two principal data formats that we work with the most. Um, and after a little recap there, I'd like to go through our pre-processing pipeline. I want to show you guys a little bit of what the raw imaging data looks like and all of the individual steps in our pre-processing pipeline that we run through. And so that'll be largely in the form of a T-shell script that feeds to a Python script, and I'll go through some of the details of what steps are going on there. And at the very end of our pre-processing pipeline, we actually feed pretty directly into our level 1 models. So level 1 models are the model that constructs what occurred on average during behaviors of interest for a single person. Um, and that data ends up being what feeds into a level 2 model, which is asking questions about groups or overall patterns within and between groups. Um, and I'll talk a little bit about and show an example of how you can parse behavioral data into a format that's usable for imaging, and we'll see how far along we get with that. So before I go any further, were there any kind of lingering questions or things people wanted me to address from the first session? No? Okay. So let me go ahead and jump back into um, the tools that we're using regularly. So, like I mentioned last time, there's three main three main components that we use or programs that we use in this process. The first one here, WinSCP, it's a file transfer protocol program that basically lets you move files up or download them from the computing cluster. Um, the second one is PuTTY here. That's a that's an interface where you can get a command prompt and log into the cluster to perform actions on the cluster itself. And last is Xming, and that's a path back from the cluster that allows you to render up graphical windows. And we'll see that in a second. So let me go ahead and start these up. So Xming just sits in the bottom here as we start up. And then we have WinSCP and extra. So what WinSCP does is it allows you to move files back and forth, but it also lets you look at the file structures in a somewhat more readable way. So one of the key things when you're launching PuTTY, which is like our command prompt, is this X11 forwarding. And I'm reviewing this again just because it's frustrating when you log in and if it's not forwarded, you can't look at any visual data. So I'll go ahead and start that up. And like I mentioned last time, when you're logging on to the cluster, it uses the same authentication system as the hospital uses, but if you do have to set up an account with them to gain access. Okay. And this is our high-performance computing cluster in the login. And just to quickly review, when we first log in, you start in a node called QMaster that lets you route yourself to other resources, but we don't like to stay in there. And this is a Linux interface, and we use a command called salloc to ask for resources, and this is covered more in the first lecture. But then we are able to log into individual computing nodes on the cluster to perform any tasks we want to do. Okay. One key thing is on the cluster, there's a modular system that lets us load programs in simply, but not load any programs we don't want in. It lets us pick which version of programs we want to run to, and that's very helpful. So one that we use a lot in the neuroimaging suite that we use is AFNI. So I'm going to use this command, module load AFNI, to bring this up. And you'll notice there's fine control over what version we're using. So it'll tell us that. And when we load in AFNI, it gives us access to a whole set of commands that we can't ordinarily use that are geared specifically towards the writing, display, and analysis of imaging data. Last, yes, sure.
Did the Baker people load the AFNI software for you?
Yes. So what they actually can load up any set or version of software into their module system that you want. It's just a matter of kind of requesting it. I think they do a basic review, but that can let you do a lot of version control, which is really nice. Because one thing in functional neuroimaging that comes up again and again is that if you run an analysis in one version of a program, there are substantive changes that happen in each version, and so results might change. And particularly now when we're in a stage in neuroimaging where replication is really important, it becomes more important to have good version control. Also, some
AFNI constantly updates, so it might change without there being like a new version. But SPM, which is another big software, they always have a SPM 3, and they put everything in there. So
yeah.
So every time the software updates, you have to tell the Baker people to update on their end.
You can put in place your own set of software that you update yourself. That's totally permissible. To put it into the module system, though, it does preserve version numbers. So you would have to request a new version when there was a major update. SPM, though, is a really good example of it making a pretty big difference. So there's people that get locked into a particular version of that program, and there's still people running SPM 99, which was developed in 1999. There's a lot of variation, but particularly when you're trying to replicate results, or let's say you started a study in one version of AFNI, you generally, unless there's a big change, you don't want to switch your software suite midstream. But people don't want to rewrite their scripts, and so things can last a long time. That's also really helpful for certain, this is a little bit of a tangent, but it's also really helpful for certain toolboxes that were developed for a certain version We also run into it a lot in terms of Python version control, so there's a lot of changes there. Okay. All right, so far we've logged into the cluster. We've asked to be allocated a node to run our processing in, and we've loaded up our AFNI suite. So I recently, yesterday, sent out a copy of our data that we're going to use for demonstration purposes here. And currently the version that I shared out is usable within this particular version of the cluster. I'm going to work on setting up a bundle so that it could be installed or looked at at home. But I'll give updates on that. But for now, the data structure here will match perfectly what you would be seeing if you downloaded that data from my drive. So currently I'm in my own personal directory, so wherever you put the directory for the workshop files, it'll change slightly in your path. So I have this folder set up in workshop, and ls lets me take a look at what's in the folder. I've saved a copy of both worked and unworked examples here, but I'm just going to go right now into this raw data folder. I have here, there's a folder denoted demo subject for demonstration subject, and I have 3 main scripts. One thing that I wanted to follow up from last time is I have a T-shell script here that's set up to pull the data from DICOM files into brick and head files. And this is a script that I wrote myself, but the individual commands are all part of AFNI. So this was one of the last things that we talked about in the previous session. But if I bring up this script, I'm using the less command. Less lets you, basically takes over the command prompt and lets you navigate through a file. So this .tcsh, I've added the extension on the end that tells me that it's a T-shell script. That's what the program here is written in. Okay. So let me make this a bit bigger. Make it a little easier on my eyes here. So we were going through this a little bit last time, but basically what this program does is, based on these variables that it sets right here, it gets information about where everything is stored that it's going to process. Then for each individual protocol that we set up, we end up with DICOMs and a whole set of series files. And series numbers are determined by what order the scanner ran things in. So with a standardized protocol, these typically don't change unless you shift something in the middle of the protocol. And in a second, I'll show you how to see the series number and what the series was named in our DICOM files, because that's one big step to review your data to make sure that the protocol names match up with what you're naming them. Because you could call this kazoo 3 and it would generate an imaging file that looked right, but if you don't double check, you don't really know what imaging data you're working with.
So by series, you mean, just to clarify, so
Yeah.
if somebody comes in for like an hour-long imaging session,
Yep.
oftentimes they'll start with a scout, and then they'll do a structural NP rage, and then they'll do a DTI, and then they'll do task 1, task 2.
Right.
So that's what you mean by series.
Yes, and specifically, the series is individual data that the scanner generates. So, for example, when we run a functional task, you get a whole set of files. You get the actual mosaic image of all of the individual volumes that got recorded, um, and then you also get some from the scanner itself. It automatically generates a series of statistics and status and logs files. And each of those, even though they're not all imaging data really, they each get like a little series number. So if you were using approaches that relied more heavily on the default data that the scanner just generates, it does some basic motion and some basic statistics. Um, and that's just sort of prepackaged. So those also get series numbers. So one thing to remember when you're looking at the rawest of the DICOM data is that you want to take the first item in the series. That's the the mosaic of image volume. So each time you went fully through the brain, that's one image. Those always come first, and then there's derived statistics and information about that series that come after. So, series 48, for example, gets this label based on what we named it in the experiment. But after series .48, there's a series .49, and that has some motion information. And then there's 50 and 51 and 52. Those are all derived from that and get the same name. So that's worth mentioning that
So
you
yeah,
should use
so
the first.
you need to pay attention when you're setting this up to exactly how things are, how the study is structured, and what comes out
Yeah.
of it. But then once you sort of have a system in place and you stick to that, you don't need to mess with this anymore.
Right. And it's always good, even when you're set, to periodically check these things. So I'll show you guys in a second how that's structured. But in this script, like I was talking about before, it runs this process, and this is all stuff. This is there's two commands that come through AFNI. This command sorts your raw DICOM files into directories based on their series number, which is really nice because it's laborious to move them yourself. And then I don't want to go too far into detail, but this is a loop that basically moves those directories around and then uses this daemon command. This is another AFNI command that basically takes the name of the folder that the DICOM files are in and makes a .brick, B-R-I-K, and a .head, H-E-A-D, file. And those respectively represent the brick file is the raw matrix of imaging data, and the header file mentions the organization information about what happened with that brick file and the history of commands run on it. And brick and head is the native format that AFNI uses. It's not really standardized. I believe that the reason that they have kept it split up is because there's a really in-depth history about everything that happened to a file in the .head extension, and that's not preserved in the other main format, which is .nii, which is the extension for the Nifty data format. And Nifty is much more standardized. That's the format that's utilized by programs like FSL, SPM, and basically it's the default that's utilized by most neuroimaging programs because our main analysis suites use NII files.
I have a question.
Sure.
So can we use the same kind of program to convert it into Nifty, or?
Yes, you absolutely can.
Okay.
So there's
but the code will change.
the code would change slightly. There's two sort of methods that you could use to do that. One would be to add a command further down to, you could first convert them into brick and head files and then convert them into Nifty. That's through a program called 3D AFNI to Nifty.
Okay.
And then that basically, if you execute that and direct it towards one of these, either a brick or a head file, it'll go ahead and convert those into NII. There's another more direct program that's used for conversion more directly from DICOMs over to directly to NII files, and that's really useful for more complex files like DTI files have some additional data, and that program is DCM to NIIX, and that was put together by NITRC, and it's like a collaborative of neuroimaging tools that they set up, and AFNI took that program and wrote _AFNI on it and made it more compatible with their tools. So that's another path that you can use to directly convert.
So we can do all this only if we could load the AFNI, right?
Correct, though you could set up a script that does all of these things. I use these AFNI commands because they're convenient, but you could easily set up a program that it would take a little more work, but you could replace this move to series directories with a command that recognized files that had a certain series number and then moved them to another folder. That's pretty convenient. You would need, if you did not have AFNI, you would want another third-party program to convert them, but you could just as easily you could download the original 3D DCM to NIIX program and replace it in
But
there.
if you're working on Baker,
Yeah.
it's all there,
Yeah.
right?
Oh,
So it's
yeah.
just a matter of kind of redirecting it. I mean, if you want to work on some machine that's not connected to Baker, then you have to have AFNI installed on it.
Okay.
But
Baker.
anything that's working off of Baker, you can access AFNI. You probably have to do
Okay.
some redirecting of
Okay.
shells,
Okay.
but it's all
But it's
there.
not, okay.
Yeah.
That makes sense.
Yeah. So on Baker, that's
already
more
there.
of an issue for if you're not on Baker.
Okay.
And actually, you'll note in this script, I've even incorporated, because I kept forgetting it, I kept incorporating this module load AFNI command, and even if I've already loaded AFNI, that's still in there. So let me move really quickly over here to WinSCP, because I want to identify something in our AFNI files.
While
But
you're doing that, just a quick question.
sure.
You're operating on all the mosaic data. You're not the mosaicing it anywhere. Is that true?
I'm sorry. I'm operating on the mosaic data.
When you launched your TCSH file,
Yes.
input file, where your raw data, where your DICOMs are sitting, those are mosaic DICOMs, or they've already been unmosaic?
I believe in their current form, they're mosaicked currently, and then in the process of that conversion with Daimon, it recognizes that they're mosaicked and then breaks them up according
so
to
you're
their.
not manually doing it.
I am not manually breaking them apart. No.
You pull the data off the scanner during mosaic one.
Correct.
Okay.
Yeah. It took us I know that because it took us a minute when we first did it to realize why our image size was so big, and it was just not parsing. Yeah. One of the switches, the DICOM org switch, helps account for that in that program. Sure. Okay, so if we take a look at, so our raw data here is stored in this folder that I made called DICOMs. This is literally what it looks like when it comes right out of the scanner except I did some processing on it, but don't worry about that. So these files are named according to the ID number, and this 4-digit number after the scan number is what the series number is. So I'm going to go ahead and open this file. And this file is a mix of data that's only machine readable and some plain text. But fortunately for us, the name of the series title here is in plain text. So if you didn't log the order that the series came in or didn't have any information based on this file, you could sort it out. It's much better to know what order everything happened, or if there was a deviation in your protocol ahead, because it just makes this part easier. But you can find the information about when the files were made and generated all in here. But I'm going to focus on the main thing that we use to find those labels. So when I said series.5 is this in my script, I can find that by searching this particular tag called T protocol name. And if I search in the file, it jumps me down here. And in this section, there's some information about what was run. And T protocol name, this is the tag in this file that says what the whoever was the technician for the scan, this is what they wrote in, or alternately what they loaded up if they loaded a standard protocol. So this is what they named this. So even if I lost track of which series numbers everything was, I could jump to this and still find it. Okay. So, each of these files are from different series. So you'll notice, I have series 6, 12, 13, 18, 23. There's a bunch of data here. Oh, I am in the wrong directory entirely. But we were in the right DICOM structure. So I was wondering why I had about 6 more files than I wanted. So here's our workshop folder. So this was the DICOM script that I was looking in. Underneath demo subject, there is this DICOMs folder. And so this looks like what we would get straight out of the scanner. There's been no folder organization. So what I'm going to do now, this is WinSCP isn't needed for this. This is just to kind of show you visually what it looks like. So if I pop back over here, I can run this DICOM script. So before I mentioned that this ends in .tcsh. In Linux, unlike Windows, the extension of your files doesn't actually mean anything as far as Linux cares. It helps to help organize things, so I don't forget that I wrote this in T-shell, for example. But when you want to run a program that's not this overall interface, if you just log in as bash, and that's just the, if you enter random commands, that's what it gets processed as. But you can also call tcsh, which is T-shell. That lets you change how programs that you send to it are interpreted. So if I run this, I get a series of input, and this will screen by pretty quickly, but it first tells you how many input files it's processing, and this goes pretty quickly. So I'll jump back up when we're done. But basically what's going on here is we're getting a report about how many volumes went into each of the series, and then it's running through my loop before that that tells me what occurred. So if I scroll back up here, there's a lot of data, so right there. So in the beginning it says, hey, you gave me 648 files to look at. This is the move to series command here, and it found these series numbers. Now, if I had raw information from the scanner and I didn't pick out these series numbers, you would get, 1, 2, 3, 4, 5, 6, 7, all the way to 63. And when it does that, it would give you a report about which of those folders has real imaging data in it and which is stats files. Okay. So then what it does is it goes in and it takes a look at the very first volume that happens in your data. And it'll give you a report about how many slices there are, a bunch of detailed information, stuff about the voxel dimensions. There's a series of warnings that it gives. There's a warning that it says about the slice-based center is different from the mosaic center. The computation of obliquity may be incorrect. So basically, it can tell that your imaging file isn't perfectly aligned into a square grid. That's all that's saying. And so it estimates how much off of a square grid it is, but that's pretty standard in imaging data. And so it just repeats this through all of the series we fed it, and that's the loop that I set up with this daemon command. It's useful to note too that all of these files get stored. So, or all of this information gets stored in the head files at some level. So I was in this raw data folder. So if I look now in my individual subject folder, before I just had a long list of DICOM files. Now here I have this folder of DICOM files. If I go into it, I still have all of those individual DICOM files, but then I also have things here. All my functional data got sorted into one file, and at the very top I also have an anatomical folder, and those have been sorted. And then what my script does is it goes up one directory, and here are the brick and head files for my anatomy file, and then for 4 runs of my functional task. So I want to show you guys a little bit what this data looks like. So before, when I set up Xming, if I run a program that has a graphical user interface, it'll the way PuTTY is set up with that forwarding, it'll go and look for a way to render your program GUI for you. In this case, the AFNI command will launch AFNI, and that'll look for a graphical user interface. And those will pop up on your screen. Just a minor procedural thing. If you close the graphical user interfaces on your screen, it won't affect anything with your session. But if you close this PuTTY window, it'll close everything down. So don't do what is surprisingly easy to do and accidentally close your PuTTY session because you brought up AFNI. Anyway, I'm going to go ahead and launch this. So here's this X11 thing, and it starts loading up AFNI. AFNI is a little bit idiosyncratic in its graphical interface, but once you start using the program a little bit more, you can start to appreciate some of the functions, but there's a little bit of a learning curve at first. What's that?
This is what you needed
Xming for, yeah, so that I could do it. So I'm going to increase the size here a little bit, and we'll go into AFNI a lot more, but we could do a whole... Huh?
Sorry,
I launched the
Or
AFNI
launched them.
command in PuTTY, and that opened them all
You
up.
just type it.
Yeah. And what AFNI does when it launches is it looks at your current directory and looks for any neuroimaging files. If it finds any anatomical files, it'll load those first. So I'll go into more depth, but these are the images for the various directions and slices that you got as part of your neuroimaging acquisition. Those can get turned on here and here. So if I click on underlay here, so underlay is the thing that's in the background of your images. You can also put new images at various levels on top of that. So I'm going to click on underlay here. So you'll notice in this little window here, there's the 5 brick and head files that I have in my current directory. There's this one, which is the anatomical, and that's what's up currently. You'll notice it says SPGR, which is denoting that it's an anatomical file. These functional files, you'll notice they're denoted as epi scans, and you'll notice it says 3D plus T. That means there's 3D space, and then also the individual voxels, the individual bits in that scan alter over time, and it'll tell you how many TRs or volumes that happened in your experiment. So, so this is the anatomical file we're looking at.
So just to clarify
Yeah.
a little bit, 'cause
Sure.
we're not
Yeah.
maybe familiar with it. Basically you get one image that looks like this, one structural image. When you do a functional MRI scan, you'll get, and so acquiring this takes about 5 minutes. Even a functional scan, you're usually getting an entire image of the brain every 1 or 2 seconds. So if you collect data for 10 minutes, you have a lot of scans, and that's what the time element is.
Yeah. Thank you for clarifying. So if I jump to my functional task, so, you know, say what you will about this. In imaging, we like to put underneath our pictures a beautiful T1 anatomical image to show you where everything is, and it looks real nice. The real functional data that we gather, though, is much lower resolution. So let me go ahead and show you what one of those functional images actually looks like under the guts. So this is the output from the functional image, and you can see that there's some commonalities. There's something that looks vaguely brain-like in here. But you'll notice that it looks kind of pixelated. That's because we get lower resolution in there. Because we're getting so many more scans over time. And that lets us see how, you know, the bold signal alters with some convolutions in relation to functional things that we are doing in the task. There are other modalities that have different resolutions. DTI, for example, looks more like an anatomical image in that you get one generated result. And there's a bunch of different modalities. We're going to focus primarily on functional for this, but each method and approach has different pros and cons. But I wanted you to see what the real raw data looks like. And that's a step that I emphasize, and every time I forget to look at the raw data, I regret it severely. Because in the raw data, you can see things that happen. We have a lot of pre-processing tools that I'll be going through, and they're all very effective. And unfortunately, that also means they're very effective at turning data that has problems into something that looks like it's okay, but isn't. So it's always good to look at your raw data. There's a QC portion that happens after we run our model that'll probably be in one of the later workshop sessions, and that does a really good job of showing you those steps. But I want to emphasize that looking at your raw data, and this is the rawest form that we can easily look at because it's just the DICOM files converted but not altered in any other way. Um, so we'll delve back into that more when we're looking at our data review steps. Okay, so if you click done twice, it'll close AFNI. It seems a little intensive to quit, but yeah. So taking a look at these brick and head files, I'm going to move up a directory here. So this is my raw data folder. So this was my DICOM script that I ran. I have two other scripts here, and these are designed to take experimental files and convert them over into a format that AFNI is expecting. So I'll cover this when we're taking a look at the actual pre-processing stream. But I would just want to show you one of these quickly. And this is written in a slightly different language. This is written in Python. It's not super complicated, but there's a couple of methods that I used for this. So this ends up being pretty detailed, so I'm going to go and a little bit specific to your individual experiment that you're running. The way we run our experiments is we do all of the data acquisition and collection on the scanner, and then there's an RF trigger that sends basically a pulse to our computer that's running ePrime, and helps us sync up our behavioral data that we collect to the actual imaging data. All right. So in order to do that, it has to be able to read in text files and run system commands like deleting and moving files. So I bring these parts into the script, and there's a function set up. And basically what this does is it assigns some variables, just like the other one. And based on what subject number I give it, it finds the directories where my data files are stored. Then what it does is it uses this CSV reader to open up this file, which is an exported text file from ePrime, and just reads it into a data structure. Then I set up a dictionary, which, to kind of abbreviate it, what it does essentially is it has one variable that's the key in the data structure, and that's the top of the data column title. Let me jump back here just a second. So this is the text file that's the output from ePrime. This is kind of a default readable format that we can use. And I'm just going to open this quickly. In Excel is the easiest way to look at this. If your trackpad doesn't betray you. Okay. All right. So ePrime output, the way it's structured, is it gives you variables, way more variables than you would ever want. But the format of the data is the first column has your labels, and the rest of the rows in the data set have your data. We can talk a little bit later about ePrime data formats, but basically this has the information about when they responded when in the individual protocol.
Can I tell you one more sort of cloud level? So people who might
Sure,
not-
sure. Uh-huh.
So what's happening, what's important for the fMRI analysis is to know when different things are happening. So there are different trials. So in this particular case, this is a go, no-go experiment. So there are a whole bunch of trials where the kids see something that's supposed to go, 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 go. And then there's trials that say, stop, don't go, stop. And what all of this is doing is taking that information of when those things happen during the 10 minutes, whether it's every 2 seconds, there's a brain scan, and logging exactly in time when those things are. And so what this is doing is integrating that information that's contained in this ePrime script and putting it with the that fMRI data. But so it's really all just about the timing and the grouping of the different types of events.
Okay, so basically it reads that file into a format where it's got the label and then all the data in the row. And this all ends up being really specific to your task. But basically I go through and determine in these loops whether this was a trial when they were supposed to respond, or this is a trial when they weren't supposed to respond, and whether they responded or not to that trial. And that ends up with 4 categories: when they were supposed to go and they did, when they were supposed to go and they didn't, when they weren't supposed to go and they did, and when they weren't supposed to go and didn't. So it categorizes their response and then determines the exact time in the same synced up time format that the fMRI uses to say when the volumes happened.
Other experiments might have something that says, this is when you saw a happy face, this is when you saw an angry face, or this is when you saw something that you subsequently remember, this is when you saw something that you didn't encode. So.
Yeah, and there's some general principles that are common in all of the ePrime files, but this is something that I wrote myself that was totally determined by what the experimental design was. And there's different methods. I liked using a Python script because it's standardized, but you could use Excel to calculate this too. The nice thing about doing it this way is you don't have to manually do work every time you run an experiment. So basically what it ends up doing at the end, and this file is in our data stuff that we've shared, and I'm happy to go through it in more detail as people are starting to kind of implement their own designs. But basically what it does is it ends up calculating the timing of when all of these events occurred, and then it outputs it to a text file. And that text file ends up looking, so this is now our study folder where we're going to process our data. And the output, I have to run my script. So if I, so like TSCH, I'm now typing, actually, strike that. So I have the secondary T-shell script. Since I wrote it as a function, you can run a whole bunch of subjects at once. And I have this short T-shell script that basically says run this Python function from within this file and run it on demo subject. So if I had 15 subjects, I could write 15 lines and send it the name of each subject, and it would run everybody. This is just an efficiency thing. You could just as easily run this from the command line on one person.
Yeah, so in general, like when you're starting a new study, all this stuff is scripted at some level. So you have to kind of start by saying, okay, there's some work up front. You take a template script and you have to tweak it to make it work for your study. And then you kind of get everything set up, and then you run the script that converts it to a file. You run another script that grabs all of your events. And so there's a little bit of work in the beginning, but then everything is pretty straightforward after that's done. But then you do sometimes have to go back and adjust and troubleshoot. But
Yeah, and really one of the primary things that there's the advantage that you get in scripting everything is if you find some oddity in the data file, or you want to analyze your data slightly differently, you don't have to start from scratch again and rebuild everything. You can just make an adjustment to the script, queue everything up, and run everybody again.
throw out all the ones that didn't respond fast enough or something
Yeah,
like that.
exactly. So I'm going to just run that brief T-shell script that runs another Python script. And this is an earlier version. I added a thing that says "done!" exclamation point, but that's not in this one. But it did actually run that file. So if I look, it wrote these 4 text files, and this is the format that AFNI's expecting for behavioral data information. So if I open one of these text files, what this is it's a series of numbers, and each of those is a time that this event happened. And it's in relation to when the scan started. So this first event here happened 6.462 seconds into the first run of this. And so there's 4 rows here, and those correspond to the 4 runs of the program, or of the task that I'm running. So those correspond to go, no go 1, go, no go 2, go, no go 3, and 4. These are...
what runs are?
Yeah, I don't think I totally mentioned that. So basically, when you're running in an fMRI experiment, frequently you want to break up your data for a couple of different reasons into separate runs for your experiment. And often these are like duplicates of each other, so you break up your experiment and you run through a portion of the experiment in each run. There's a couple of advantages. There's some technical ones. So there's some like kind of drift effects that you get eventually. If you run somebody really long in the scanner, there starts to be more problems and issues related on kind of a practical kind of level. If you break your experiment up into shorter runs, the person in the bore has less time to move around from when they started. Movement's very important to minimize. Also, if there's kind of a technical issue with one of the runs and something goes wrong, but you don't have time to try and reacquire the data in your protocol, you can use good quality data from 3 of your runs if one of them failed, and you can still have data from that subject.
So basically, if you have an experiment that requires, say, 20 minutes of data collection, it's best to split that up into 4 different runs from just kind of like this, these sort of 4 or 5 minute runs. It's exactly the same. Everything is really balanced and the same, but it just is cutting it up into different chunks.
Okay, so when you say runs, you mean like splitting it up from a localizer to an MP range? Is like those are separate runs or multiple runs of the same thing?
So there's a little bit of a nuanced answer to the question. So usually when we're talking about runs, we mean within the same experimental paradigm, you have one series. So like, let's say you had a 20-minute experiment. I want to divide it up into 4 5-minute chunks. The first 5-minute chunk is the first run. The second is the second run so on. So you get 5 minutes of the experiment in the first one, the next 5 minutes, 15, 20. And that's the total of your experiment. So generally in the nomenclature, that's considered 4 runs. When you move to like a different series, like the anatomical versus the functional, usually you don't think about that as runs. Those are like separate series that you're running. But on the functional end, you end up with a head and a brick file for each run, and you get one for your anatomical. So they're similar in that way, but when we talk about runs, usually what we're referring to is chunks of an experiment.
Yeah, so for this experiment, for example, the subject goes, this is a leak protocol has, so someone will have sat down with Mark and got all the stuff on the computer all the sequences programmed out in the computer in the scanner. Subject goes in. The first thing that happens is there's a scout, there's some preliminary things, shimming, things like that. Then we do an MP rage, and a lot of times that's sort of automatically done. I think we do a DTI on these guys, and then we say, okay, now we want to do go, no go, run 1. Then they'll run through that, the scanner will pause, and then we'll say, okay, let's do go, no go 2. And so that's like all there. You can sometimes say, this kid is just moving so much, there's no way he's going to get through go, no go. Let's stop after 3 runs. And then you can just say, okay, now let's launch the second experimental paradigm we're looking at, which was the face memory. So let's do the face memory for this kid right now.
So is that why you guys have the additional trigger setup so that you can run those multiple runs with E prime?
So each run, because the timing is so critical, the functional runs have a trigger. So and each run has its own trigger.
Yeah.
So it's like all set up, everything's ready to go, and then when the scanner gets to a certain, starts collecting data, the pulse begins it. Yeah. So there's always a separate trigger for each run.
Okay.
I have one more.
Sure.
Is this the 4 run is the same experiment, or each one is like I mean by experiment is the task is the same, or do they change the task on each run?
Well, so that's part of when you're designing the tasks
Okay.
themselves, and that's sort of up to the experimenter.
Okay.
So usually we try to keep them as completely the same as possible.
Okay.
Sometimes you put different, you don't want them to have, if you want to completely randomize, sometimes you want to be careful not to over-randomize. But yeah,
Okay.
and that's all set up on the level of the sort of the E prime.
E prime.
So the only thing that from the scanner perspective is we have 4 runs. Each one is 200 volumes, 400 seconds long, something like that.
Okay. Like how
Yeah.
we have on the clinical, let's say one run is like verb gen and the other run is
Yeah.
word gen, but
Yeah.
it's like same, like language task, but then
Yeah, yeah.
it's a little
Yeah.
bit different.
Yeah.
It's
Yeah.
the same way. Right?
Yeah.
Yeah.
So for example, in this go no go task, in this case the difference between the runs, the stimuli is identical, the thing we're asking them to do is identical. The only thing that really varies is the randomization is slightly different, timing wise of when the events occurred between those, but otherwise they're identical. Other tasks, there's a little bit more variation, but usually they're tied together by more common elements than they are different. Other people sometimes will break up the task and kind of be doing a slightly different task between runs. That's maybe a little more common in block design, but it's really just what your experimental objective is with your experimental design of the functional task, what you're trying to get. Okay. So I want to tease before we leave today the pre-processing script. So the running the onset pull file and the DICOM script file together, those pull they pull the raw imaging and behavioral data out into a format that can be used in our script to pre-process the data and run the level ones. They're kind of combined in our pipeline framework here. Um, so those are the stages to get the raw data out. Now at this point, we're looking at the actual pre-processing script. So you can set up your directories differently, but we tend to organize by task, and then we have subdirectories. Some contain subject data, and some contain our scripts. So I just want to show you what our script looks like. So this demo subject.tcsh, this is a copy that's standardized across all of our subjects, except we change what the ID number is. We tend to break our pre-processing scripts up into one file for each subject, because we often run into a problem where we don't have all 4 runs, for example. And if we individualize the T-shell, we can run data for somebody whose data isn't incomplete. If we just ran the same thing for everybody, it would throw us an error when we tried to run somebody whose data differed in any way. So just really quickly, I want to open up this T-shell file. And in this T-shell file, it's really a wrapper for a program within AFNI that runs pre-processing. So at the beginning, we have our identifier here that says that this is a T-shell script. And then we have a bunch of set commands. The pound signs here are comments, so they don't actually get run. They're just notes. So in this file, we start out by setting a bunch of variables that tell us both where our subject directory is and some parameters and things that we want to easily vary in between subjects. And then we call this AFNI procpy command, and there's a whole bunch of switches. These slashes just carry the line on, so really this would be one huge giant block of text. And this contains all the pre-processing steps that we're planning on running, as well as the regressions to run our level 1 data. So there's a lot of information here, and I want to show all the steps, but that's a whole workshop session on its own. So I want to spend the next session diving deep into this script, running it and showing some stages of the output, and then I'll also probably in this session following that go through the data quality checking and other related issues. So that's the general overview. Are there any last minute questions we wanted to ask specifically about material we talked in here?
So can they practice doing this?
Yes, so currently there's, currently you can, if you have access to the cluster, you can download all of the raw data that I set up and sent out in the Google Drive link. You can upload that to the cluster, and so as long as you have cluster access, you can set that up in your personal user folder, and you should be able to run through all the steps. And if people are trying to run through all the steps and you have questions, feel free to send me an email. I'm happy to take a look as time allows to try and get everything set up.
So did you send us the script too?
As part of that package, it includes basically all of the contents of the folder. So it's raw DICOM folders and all the associated scripts in the directories they're supposed to be.
Okay.
So yeah, on your own, you as long as you have access to everything, you should be able to run through those steps. And I've tested it a couple times, so it should work.
Okay.
But there's always, especially when you're first getting things set up on working with the cluster and all of these programs, occasionally there's little settings that are a little bit iffy. So I'm happy to walk through people getting trouble trying to run the things. Okay. Cool. All right. Thanks.
Thank you.